The Nakajima Sakae engine powered the legendary Zero fighter that dominated Pacific skies in 1941 to 1942, earning a fearsome reputation among Allied pilots who faced Japanese aerial supremacy. But declassified records and post-war engineering analysis reveal the Sakae's success concealed fatal compromises. Weight reduction obsessions that sacrificed durability, manufacturing quality that couldn't meet design precision, fuel limitations that strangled performance, and mechanical fragility that killed pilots under sustained combat operations. The engine that won early battles carried the seeds of Japan's aviation defeat from the moment it entered production. The Nakajima Sakae's origins trace directly to American technology that Japan licensed and adapted during the 1930s, when Japanese aviation industry sought to close the performance gap with Western powers. Nakajima Aircraft Company purchased manufacturing rights to Pratt & Whitney radial engine designs, gaining access to technical specifications, metallurgical formulas, and production methodologies. The licensing agreement provided complete documentation for 9-cylinder and 14-cylinder radial configurations that American engineers had spent years perfecting, giving Japanese designers a proven foundation rather than requiring development from fundamental principles, and the Sakae retained core architectural elements from Pratt & Whitney designs, including cylinder spacing, crankcase structure, and valve timing configurations. Japanese engineers modified the licensed designs to emphasize different priorities than American specifications. Where Pratt & Whitney optimized for reliability and durability suitable for commercial aviation and military operations requiring sustained performance, Nakajima focused obsessively on weight reduction. Every component was lightened, simplified, or eliminated if deemed non-essential for achieving maximum power-to-weight ratio, creating an engine that produced impressive horsepower relative to its mass, but sacrificed the robustness that American designs incorporated for operational longevity and combat survivability. The Sakae 12 that entered production in 1940 produced 940 horsepower, while weighing just 1,200 pounds. Remarkable specifications that enabled the Zero's legendary performance. But the weight savings came through systematic removal of safety margins, use of minimal material thickness, and elimination of redundant systems that American engines included, creating fundamental fragility that wouldn't become apparent until sustained combat operations revealed how the design choices that enabled early success contained the mechanisms of eventual failure. Official Japanese histories described the Sakae as indigenous development, minimizing the American technological foundations. Post-war analysis revealed how extensively the engine relied on licensed Pratt & Whitney architecture, while Japanese modifications focused primarily on weight reduction rather than performance enhancement. But the American origins were just the beginning of compromises. Japanese aviation doctrine in the late 1930s prioritized maneuverability and range above all other considerations, creating design philosophy where every pound saved translated to tactical advantages. The Sakae engine embodied this philosophy through systematic weight reduction that compromised virtually every aspect of reliability and durability. Crankshaft counterweights were minimized to barely adequate mass, connecting rods were machined to minimum structural thickness, cylinder wall thickness was reduced to levels American engineers considered dangerously inadequate, and accessory drives were simplified by eliminating components deemed non-essential, creating an engine optimized for short-duration peak performance rather than sustained operational capability. The crankcase used magnesium alloy rather than aluminum to save weight, but magnesium's brittleness made it susceptible to cracking from vibration and thermal stress. Under sustained high-power operations, crankcase fractures became common failure modes that American aluminum crankcases rarely experienced, and repairs were difficult because magnesium welding required specialized equipment and expertise that forward maintenance facilities often lacked, meaning crankcase damage frequently resulted in complete engine replacement rather than field repair. Bearing systems received inadequate lubrication capacity to save weight from oil system components. The Sakae used minimal oil capacity and simplified distribution compared to American engines of similar power output. During sustained combat operations requiring maximum power for extended periods, oil temperatures would spike dangerously as inadequate cooling capacity couldn't dissipate heat generated by bearings under stress, leading to oil breakdown that accelerated bearing wear and frequently caused catastrophic seizures that gave pilots no warning before total power loss. The supercharger system was simplified to single-stage configuration that saved weight but limited altitude performance compared to two-stage designs American engines increasingly adopted. This design choice meant the Sakae maintained power only to approximately 14,000 feet, above which performance degraded rapidly, creating tactical disadvantage against American fighters operating effectively at 25,000+ feet, where Japanese aircraft struggled with engines that couldn't deliver adequate power in thin air. Yet weight savings meant nothing when production quality collapsed. The Sakae's sophisticated design required manufacturing precision that Japanese industry struggled to achieve consistently, especially as wartime pressures forced production acceleration while skilled workers were conscripted into military service. Cylinder bore tolerances specified in 10,000ths of an inch proved impossible for many Japanese factories to maintain with available machine tools, creating dimensional variations that affected compression, oil consumption, and bearing clearances, essentially guaranteeing that production engines would perform worse than prototype specifications regardless of design quality. Quality control systems collapsed under production quota pressures as military demand escalated. Inspectors faced impossible choices between rejecting defective engines and meeting production targets that factory managers treated as life-or-death obligations. Engines with dimensional errors, surface finish problems, and assembly defects were approved for delivery because rejecting them meant failing quotas, and wartime Japan's military culture treated production failures as sabotage, requiring harsh punishment, forcing inspectors to approve engines they knew contained defects rather than face accusations of undermining the war effort. Material quality degraded throughout the war as strategic shortages forced substitution of inferior alloys for specified materials. Connecting rods designed for high-strength aluminum alloys were manufactured using available metals that couldn't withstand design stresses. Valve springs made from substitute steels failed prematurely, piston rings wore rapidly due to improper heat treatment, and fasteners broke under vibration because metallurgy couldn't replicate specified material properties, creating cascading reliability problems where each component failure accelerated stress on remaining systems until catastrophic failure became inevitable. Nakajima production facilities in 1944 to 1945 operated under conditions making quality control impossible. Allied bombing disrupted supply chains, destroyed precision equipment, and forced production dispersal to improvised facilities. Workers assembled engines in unheated buildings without proper lighting or measurement tools, using hand filing to fit components that should have been precision machined, creating engines that might run initially but were guaranteed to fail quickly under operational stress. Yet they were installed in aircraft and flown by pilots who had no idea their power plants were fundamentally defective. Poor construction was deadly, but the real crisis was fuel. The Sakae was designed to operate on 92-octane aviation fuel, but Japan's petroleum refining capacity could produce only 87-octane fuel consistently, with quality degrading further as the war progressed and synthetic fuel production increased. This fundamental mismatch between engine requirements and available fuel meant the Sakae never achieved its design performance specifications in operational service. Running on fuel that caused detonation under high power settings and forced pilots to operate at reduced manifold pressures that prevented engines from producing rated horsepower. Detonation, uncontrolled explosive combustion rather than smooth burning, destroyed pistons, cracked cylinder heads, and damaged bearings when pilots attempted full power operations on low-octane fuel. Japanese pilots learned through bitter experience that pushing throttles to maximum resulted in rough running, power loss, and frequently catastrophic engine failure, forcing them to self-limit to perhaps 85% of theoretical maximum power to prevent detonation damage, effectively reducing combat capability by 15% simply due to fuel quality limitations. As the war progressed, fuel quality deteriorated catastrophically. Synthetic fuel plants produced inconsistent output with octane ratings sometimes falling to 80 or below. Contamination from inadequate refining processes introduced impurities that fouled spark plugs, clogged fuel filters, and corroded fuel system components, creating maintenance nightmares where engines required constant servicing simply to remain operational regardless of combat damage, and many aircraft were grounded not from battle damage but from fuel system failures caused by substandard aviation gasoline. American technical intelligence testing captured Sakae engines after the war using proper 92-octane fuel revealed performance significantly exceeding what Japanese pilots had experienced operationally. The engines ran smoothly at power settings that would have caused detonation on Japanese fuel, demonstrating that fuel quality limitations had crippled Sakae performance throughout the war, essentially guaranteeing that even perfectly manufactured engines couldn't achieve design specifications because the fuel they burned wasn't adequate for the compression ratios and supercharger boost pressures the design required. Even with perfect fuel, one fundamental flaw remained unfixable. Combat operations revealed the Sakae's fundamental fragility under sustained high-power operations that peacetime testing never adequately simulated. The engine could produce rated power briefly, but extended combat requiring maximum performance for 10 to 15 minutes caused overheating, vibration, and mechanical stress that frequently resulted in catastrophic failures. Main bearing failures were particularly common and deadly. Inadequate lubrication under sustained high RPM operations caused bearings to seize without warning, stopping the engine instantly and frequently causing crankshaft breakage that destroyed the entire power plant, giving pilots no opportunity for emergency procedures before their aircraft became unpowered gliders over hostile territory or open ocean. Cooling system inadequacies plagued Sakae operations throughout its service life. The cowling design that provided excellent streamlining for maximum speed proved inadequate for cooling during sustained combat maneuvering at lower airspeeds. Cylinder head temperatures would spike dangerously during prolonged dogfights, causing pre-ignition that damaged pistons and valves, and pilots reported being forced to reduce power during critical combat situations simply to prevent engine destruction, surrendering tactical advantages to preserve their power plants and essentially fighting with one hand tied because their engines couldn't sustain the performance the tactical situation demanded. The lightweight construction that enabled impressive power-to-weight ratios proved catastrophic under battle damage. A single rifle-caliber bullet striking the crankcase could crack the magnesium alloy, causing immediate oil loss and rapid engine seizure. American pilots learned that Sakae-powered aircraft were vulnerable to battle damage in ways that radial-engine American fighters weren't, Hits that would merely reduce power in a right cyclone, or Pratt and Whitney, would completely destroy a Sakae, giving Zero pilots no survivability margin when damaged, and this fragility meant Japanese pilots couldn't afford to absorb damage the way American pilots could, creating psychological pressure that affected combat decision-making. Maintenance requirements exceeded Japanese logistics capabilities. The Sakae required frequent overhauls, officially every 150 hours, but operationally engines rarely achieved 100 hours before requiring major maintenance. Forward bases lacked facilities, tools, and parts for proper maintenance, forcing mechanics to improvise repairs using inadequate equipment and substitute components, creating a maintenance death spiral where poorly maintained engines failed more frequently, requiring more maintenance that couldn't be properly performed, accelerating the degradation that eventually grounded aircraft not from combat losses, but mechanical exhaustion. Pilots knew the risks, but desperation forced continued use. Nakajima engineers recognized the Sakae's limitations and developed improved variants attempting to address performance and reliability problems. The Sakae 21 introduced water methanol injection for emergency power boost and improved supercharger for better altitude performance. But fundamental design constraints prevented meaningful improvements. The lightweight construction that defined the Sakae couldn't support significantly increased power without catastrophic structural failures, and attempts to strengthen components added weight that negated the power increases, creating an engineering trap where every improvement undermined the characteristics that made the original design successful. Production of improved variants faced insurmountable obstacles as Japan's industrial situation deteriorated. Manufacturing the more complex Sakae 21 required precision and materials that weren't available. Factories received specifications for improved engines but lacked the machine tools, skilled workers, and quality materials to build them properly, resulting in engines that nominally were upgraded variants but actually performed worse than earlier production due to manufacturing quality collapse, and pilots sometimes requested older Sakae 12 engines rather than newer variants because the earlier, simpler designs were more reliably manufactured. By 1944, Sakae production had declined catastrophically in both quantity and quality. Allied bombing destroyed Nakajima facilities, while submarine warfare cut off raw material supplies. Engines arrived at combat units with obvious defects, rough running, oil leaks, low compression, that would have resulted in rejection in 1942 but were accepted in 1944 because no alternatives existed, and many aircraft were grounded immediately upon delivery awaiting engine repairs before they could fly their first combat mission, creating the absurd situation where Japan possessed aircraft but couldn't field them due to engine problems. The Sakae 31 and later variants designed for improved fighters like the A6M50 incorporated lessons from earlier failures, but arrived too late and in insufficient numbers to matter. American industrial capacity was producing engines in quantities and quality levels Japanese industry couldn't approach, meaning that even if Nakajima had solved all the Sakae's problems, numerical and technological disadvantages would still guarantee defeat. By 1944, the Sakae's legacy was written in losses. The Nakajima Sakae's historical legacy embodies aviation's central paradox. Optimizing for one set of conditions can create fatal vulnerabilities when circumstances change. The engine powered Japan to stunning victories in 1941 to 1942, when combat consisted of short-duration intercepts against unprepared opponents, but the same design choices that enabled early success — extreme lightness, minimal durability margins, simplified systems — guaranteed failure during the sustained attrition warfare that developed as American forces adapted and industrial capacity tipped decisively against Japan. Early combat validated the design philosophy completely. Zero fighters powered by Sakae engines dominated Allied aircraft through superior maneuverability enabled by remarkable power-to-weight ratios. Japanese pilots achieved kill ratios exceeding 10-1 during early campaigns, creating mythology around the Zero and Sakae combination that masked fundamental weaknesses, and this early success created complacency that prevented recognition of problems until circumstances changed and the flaws became fatal rather than merely theoretical concerns about sustained operations nobody had yet experienced. But modern war rewards sustainable industrial production and operational durability more than peak performance, and the Sakae embodied opposite priorities. American engines were heavier, more complex, and less efficient on paper, yet they could be mass-produced reliably, operated for hundreds of hours between overhauls, and survive battle damage that destroyed Sakae engines instantly, creating compounding advantages where American aircraft availability increased while Japanese operational readiness declined, despite possessing nominally superior fighters on specification sheets. The Sakae ultimately represents how tactical excellence without strategic sustainability leads to defeat regardless of initial success. The engine that powered Japan's greatest aerial victories also guaranteed eventual defeat through design choices that prioritized short-term performance over long-term operational capability, demonstrating that wars are won not by the best aircraft in individual combat, but by sustainable systems that can replace losses, maintain operational readiness, and adapt to changing circumstances. Capabilities the Sakae and Japanese aviation industry fundamentally lacked. The Nakajima Sakae powered early Japanese aerial dominance through extreme design optimization that sacrificed everything for lightweight performance. But weight savings, manufacturing quality collapse, fuel limitations, and mechanical fragility under sustained operations guaranteed the engine couldn't support prolonged warfare. The Sakae won battles but lost the war by embodying priorities that tactical success required, but strategic victory demanded abandoning. Watch the next video for vintage planes for more aviation truths.